Okay, so hey guys, how's it going? So today I'm going to be going through a video on the topic of radioactive decay. And I have 12 questions to go through today, but they're subdivided into subparts. So I end up covering a lot of breadth with respect to the topics on the section. So without further ado, let's begin. Okay, so I tend to go through like definitions and formulas at the beginning, and then I start to get into harder calculations. So let's go with that. So part A, what is the definition of decay constant? Decay constant is the fraction of the number of atoms that decay in a unit time. What are the units of decay constant? They're inverse seconds. What is the definition of activity? So activity is a rate of at which a source of unstable nuclei decays, or decays per second. And then what are the units of activity? So there's two units. There's the becquerel, which is 1 disintegration per second, or the Curie, which is 3.7 times 10 to the 10 becquerels. So I would remember that conversion. I think the definition of activity is intuitive, just because of how becquerel is defined, 1 disintegration per second. Okay, so problem 2. So what is the short form formula for activity? So activity is the decay constant times the number of particles. What does the half-life mean? It's the expectation value of the time required for 1/2 of the initial number of nuclei to disintegrate. What is the mean life? It's the average time for an individual radioactive nucleus to decay. And what's the formula for half-life? So half-life is equal to 0.693 over the decay constant. What's the formula for mean life? So mean life is equal to 1.44 times the half-life. So I'd memorize short form formula for activity, half-life, and also mean life. These are all very important formulas. Okay, so let's start to get to some calculations here. So problem 3, we have 1 gram sample, carbon 14 has a molar mass of 168.15 grams per mole, and an activity of 1.373 times 10 to the 10 disintegrations per second. So what is the decay constant? So the formula from last slide, activity is equal to decay constant times the number of particles. So in our question, we have our activity. We want the decay constant, but we don't have the number of particles. So that's what we're going to be calculating. So the way I memorize, so we have to calculate moles. The way I memorize moles is equal to, if you remember from chemistry, I memorize it as m over mm, mass over molar mass. Because that could be something. I mean, you're probably going to use it again, in radiological physics. If you didn't already use it lots in chemistry. So, 1 gram sample, 168.15 molar mass. We get our number of moles. Now, to get the number of particles, we have to multiply it by Avogadro's number. So let's do that, which is 6.02 times 10 to the 23. And we get our number of particles. So now we have activity, number of particles. We can solve for a decay constant. Activity, over our number of particles, decay constant. And there's our answer. Okay, problem 4. So what is transient equilibrium? So transient equilibrium occurs when the half-life of the daughter is much shorter than the half-life of the parent. What is secular equilibrium? So it occurs when the half-life of the daughter is very much shorter compared to the half-life of the parent. So if we wanted to write it in terms of decay constant, let's say, because this comes up, this is actually a pretty common question. They'll do it in terms of decay constant or half-life, but it could go either way. How would it look? And with an inequality sign. So for transient equilibrium, it would look like this. And then what would it look like for secular equilibrium? Look like this. So if you remember the formula for half-life, which is inversely related to the decay constant. So my recommendation for you would be to memorize, like if you have to memorize what is transient equilibrium, I would just memorize it in terms of half-lives, because I think it's more intuitive that way. So you say transient equilibrium, half-life of the daughter is much shorter than the half-life of parent. Secular equilibrium, half-life of the daughter is very much shorter than the half-life of the parent. And then if they ask you for, with respect to decay constant, I'd say just use this formula. You know, it's inversely related to get the answer. Just to keep things simple. Okay, so now we're gonna draw them on a plot. So I'll go through the different scenarios. I'll show a drawing, and it's actually a pretty common question to show the drawing and then you say where it is, or to draw. Like they give you the relationship and then you draw the graph. So activity is along the y-axis. Student and parent-daughter is what we're going to draw. And half-lives is the x-axis. So let's draw. There's going to be 4 drawings, 2 more after this question. But so what are the parent-daughter decay schemes? For A, so the decay constant of the parent is greater than decay constant of the daughter. So if we wanted it in terms of half-life, half-life of the parent would be less than the half-life of the daughter. It would be inversely related. So this is what it would look like. Now let's draw our plot. Decay constant of the parent is less than decay constant of the daughter. So if I wanted it in terms of half-lives, switch the inequality. Decay constant, or sorry, half-life of the parent is greater than the half-life of the daughter. So it would look like this. Look with respect to the x-axis, number of parent half-lives. You know, it's quite a difference. But now let's get to the equilibrium situations. Let's draw them. Same x-axis, y-axis. But just to start to show you the concepts. So transient equilibrium, let's do that one first. Actually, let's show them both. So for transient equilibrium, half-life of the parent is, you know, is much greater than the half-life of the daughter, and then this one would be way greater. So look at the scale. Oops. You know, as the number of parent half-lives is small, as soon as the half-lives go up, the daughter reaches it. Bam. So in this case, we're saying the half-life of the parent is way greater than the half-life of the daughter. This is for secular equilibrium. Look at the scale. The number of parent half-lives is just small. They're in decimal. So as soon as it goes, bam, it reaches it. So see, I like these plots particularly because I think they like over exaggerate the situation, so you can clearly tell the difference. Also, they're colored, and I think they're nice to look at. So let's go to problem 7. So what is the basic formula for the ratio of initial activity to the activity at a later given time? So this is the initial activity. Remember, activity is decay constant times number of particles. You could write this just as the initial activity, A is 0. This is going to be the activity at a later time, A. And typically, you could see this formula, A here, A0 would be over. Okay, let's do a quick calculation. Oh, and you're going to want to memorize this formula, definitely. So given initial activity of 1 millicurie of F18, what's the activity in 30 seconds? What would it be? We have the half-life, it's given to us in minutes. So in our case, I see that the time is given in seconds, the half-life is given in minutes. So first thing I'm going to want to do is convert to seconds, just so these things will match up when I put it in there. Convert to seconds. Okay, 110 minutes, 60 seconds a minute, and I get 6,600 seconds. Okay, so now I have the half-life in seconds. Let's find the decay constant. Half-life is equal to 0.693 over decay constant. So solve for the decay constant. I have that. Now we can, we have the initial activity, we have the decay constant, and we have the time. So we can sub them all in and get our answer. Here we go. And our answer is 0.997 millicurie. Now, that doesn't seem like much. So is that correct? So if we kind of look here, what is the activity? We know that the half-life is 110 minutes. So that's long as compared to in 30 seconds. So yeah, that is about right. I mean, sorry, that is correct. Okay, so problem 8, and we're gonna talk about parent-daughter radioactive relationships. So what is the formula for the parent-daughter activity ratio? This is the formula. This is another formula you're gonna wanna memorize. Oops. And write it down on your formula sheet. Now, depending if you're using different sources, different textbooks are actually going to write this in different ways. And it can actually make things a little bit more confusing. They may also, I would recommend, you just use this formula and make it simple. Write this one down. This is the, so decay constant 2, that's the daughter. Decay constant, this is the parent. Decay constant 1. The rest, I think, is self-explanatory. Time. This is daughter, number of particles. So I would memorize that. So part B is, what is the formula for the parent-daughter activity ratio when the time is much greater than Tm? Tm is the time at which the daughter reaches maximum activity. So this is also known as equilibrium. So what's the formula? So in this case, you can, this ends up equaling 1. So you can essentially get rid of it. And this is what you'll have for your formula. But, I think from a student's perspective, when they're answering problems, they're always tempted to automatically use this formula. But, so they'll often like memorize this formula. They may not memorize this one. And they're always quick to use this one because it looks nice and simple. But remember that this relationship has to hold to use it. Also, if you just memorize this formula, if this event occurs, this will equal it to 1 anyway. So memorize this formula. Don't so much as worry about that one. So part C, what is the formula for Tm? And this is the time at which the daughter reaches a maximum activity. So this is the formula. So Tm is equal to ln decay constant 2, which is the daughter over the parent. and so forth. So I would also memorize this formula. Okay, so what I have here is that I decided to work out just that this equals 1 in this case, which is when the time is greater than the TM, which is the time at which the daughter reaches maximum activity. So I just kind of worked it out as an example, in case you wanted to see it. So decay constant parent, daughter. This is I calculated the TM. All I did was throw these two numbers in this formula and solve for TM. I said a time 1,000 seconds. It says time has to be much greater than TM. That's pretty good. I worked it out in this formula, and it ends up being 1 minus this amount, which is approximately 1. So it does go to this formula. So in this case. Okay, so problem 9. Calculate the ratio between the parent, which is radian, and daughter, which is radon. Activities at equilibrium. So equilibrium, we can use that short form formula. So this is it's at equilibrium. So in this case, we just sub in the decay constants. And we get our answer. So part B, calculate the time when the daughter reaches a maximum activity. So that's that the other formula from the last slide. Sub in the decay constants, and we get our answer, 65.9 days. Okay, so let's go to problem 10. So given a time of 1 minute, and for the parent, the mass being 10 grams, molar mass is 127.6 grams per mole, and the half-life is 1.08 times 10 to the 5 seconds. And for the daughter, the decay constant is 9.97 times 10 to the negative 7 seconds. Let's calculate the activity of the daughter. Okay, so we're going to need to calculate the decay constant first of the parent because it's not given. So here's the half-life. And then we're going to calculate the decay constant. And we get our value. So now we need, well, there's our formula that we're going to be using. Now we need to calculate the number of particles of the parent based on moles is equal to m over mm, which is mass over molar mass. So we sub in the values, and we get our moles. Now we'll multiply it by Avogadro's number, and we have our number of particles now. Okay, so now we have everything we need. We can sub in all the values in this formula and then solve it for the activity of the daughter. So let's do that. Here we have the decay constant. We have, this is the decay constant of the parent. This is the number of particles. Decay constant of the daughter, just from here, decay constant daughter. Once again, decay constant parent, and then we just sub in the rest. There's the time, which is 1 minute or 60 seconds, so it all works out. Now we calculate it out. And we get our answer of 2.14 times 10 to the 13 particles per second, or becquerel. Okay, now for problem 11 and problem 12, I have like 4 short calculations, but they're nice calculations because they can kind of give you some like some different perspectives on how to use the formulas. I think it's very valuable when you're learning it. So let's work through the first problem of problem 11. So palladium, the dose was delivered on Tuesday at 6 a.m. If the dose is measured on Wednesday at 2 p.m. and it is 100 millicurie, the activity at 6 a.m. on Tuesday was what? And we have a half-life of 17 days. Okay, so we have our formula for activity. And notice that we're dealing with time, so I'm going to put it in hours. Half-life's given in days, so I'm gonna convert it to hours. So this is 17 days times 24 hours is 408 hours. Now I need a decay constant, which is 0.693 divided by 408 hours. So I get my decay constant in hours. Now my time difference from Tuesday at 6 a.m. to Wednesday at 2 p.m. is equal to 32 hours. So that's going to be my T. So now I can sub in my values to the formula. So now I can sort of multiply this out, solve it out. I get 100 millicurie is equal to the initial activity times 0.95. And I get my answer being 105.3 millicurie. That's my initial activity. So why this is a really neat problem is that it's giving me the activity at a later time, and then I'm working backwards to solve the initial activity. So, that's kind of a neat perspective on the calculation. Okay, so for the next question, a patient is injected with 100 megabecquerel with a half-life of 124 seconds. Now, if there is a 10-second delay in administering the injection, what's the actual activity injected? So we have our formula for activity. Now we need to calculate our decay constant again. 0.693 divided by the half-life, which is equal to 0.006 seconds to the negative 1. So now we can plug in the values within the formula. So activity is equal to 100 megabecquerel E to the negative, and this is our time, which was 10 seconds, and this is the decay constant. So we get our answer, which is 94.2 megabecquerels. So at first, that seems like a big difference. Like in 10 seconds, it made that big of an activity difference. But if you look at the half-life is 124 seconds. So now it does kind of make sense. Okay, so first question in problem 12. So if a radionuclide decays 1% per hour, how long will it take to decay to 1/2 of its original activity? So the trick here is being able to write the 1% per hour as a decay constant. So basically, what you do right off the bat is you write it as like a fraction. So 1% per hour, so 1 over 100. Now for the decay constant, but now we want it as a decimal. So 0.01 hours to negative 1. So from here we have the decay constant. We can plug it into the formula for half-life. So we get 0.693 over our decay constant. We get 69.3 hours. Now you could actually solve this. You could solve this question with the other activity formula for activity from initial and at a later time. In that case, what you would do is you would you would take the activity at a later time to divide it by the initial activity, and you would make that equal 0.50, making that the half-life, and then you would go equals e to the exponent negative t times the decay constant, and you would work backwards for the amount of time. So a longer way of doing it, but you could solve it both ways with both activity with the other activity formula, and this one is with the half-life formula. Okay, so next question. So for iodine 125 implant, the half-life is 60 days. 100 seeds are required. But if the procedure is now delayed for 7 days, the same batch is used. Number of seeds now required is, so we have time and half-life, but we're going to need decay constant. But here's our formula. Let's calculate the decay constant, and we'll do it in days because the time is in days. So 0.693 over 60 days. Time, 7 days. So here we can work out this value. So we get 0.92. So what's interesting with this problem is that it doesn't give us an activity, it gives us implant 100 seeds are required. So how I would solve this question is I would, I know that this is equal to 0.92. I would take activity divided by the initial activity. I'd move the A0 over the A. So I know that if A0 is 100, I know that in this amount of time, the activity would be 92, which is, it would be equal to 0.92. So I basically, I set up a ratio now. If 100 seeds are required, I would divide it by 0.92. And now I get my total amount of seeds, which is 108 seeds. So interesting question, because it doesn't, you're not using activities. You could solve this question in a number of ways. But I mean, through my ratio idea, I know that the activity is down to 0.92, so I would set up a ratio now. But you know, the important part is that these questions, they give you, I think, a different perspective on the activity formula. You get to see a lot of different possibilities. So it's very valuable to the student when you're first learning the material. You know, you learn the concepts, you know, then you work through the calculations. But in this case, you know, I'm providing like a, you know, many different styles of questions. So I think it's really good for the student who's learning the material. So with that being said, I'd like to thank you for viewing. Good luck studying. And that's all. Thank you very much. Bye.